The next speaker I would like to introduce is another Martin. Martin is a postdoctoral researcher who's actually joining us for him in the middle of the night from Japan. He works in the mathematics computer science lab, and he will tell us a little bit more about an interesting difference that he's recognized. Martin, the stage is yours.
Thank you so much for your kind attention. Good night from Japan, everyone. I'd actually like to pick up where Florian got us, but a little bit before. Florian talked about the coronavirus, and I'd like to ask you, do you recall a time before Corona where we would not get out of bed and directly into the home office, but instead we would all cram into our cars and sit in traffic jams for hours? And I'm asking you, wouldn't these times be way more productive if we could spend them in self-driving cars? You could get your emails out of the way during your commute to work, for instance. But then there's headlines like this one, which don't exactly inspire trust. So tonight we're going to unpack some of these challenges that self-driving cars are facing. And we're going to do this in a way scientists love to do. First, we're going to simplify. So here's a robocar, and here's a cube. And what we're going to do is we're going to teach robocar to recognize the cube. Robocar has some cameras and depth sensors to scan it, but because of some inevitable measurement errors, it won't see this nice clean cube. It will see a distorted thing, which we call a noisy cube. And because it can't map this noisy cube to the clean model it has, it will say, well, there's no cube to be seen. And this is where we started our research, asking, can mathematics help to recognize this cube? And we're going to borrow a setting from physics here. We have a glass with some ice cubes, and over time, these ice cubes will melt, and we'll end up with some nice and cool water. So the temperature in this glass is averaging out. And we're going to use this exact same process of averaging, but we're going to apply it to the distorted cube. So here's our setting. On the bottom right, you see the target where we want to get, the clean cube. And on the upper left, you see this distorted cube that robocar sees. And giving it some time, we actually see that the bumps are getting reduced. It's looking nicer and smoother and better. And it's given some more, well, okay, this is not in the right direction. Stop it, algorithm. Stop it. Oh boy. Okay, this is clearly not a cube. This is a ball. So I guess we should have told the algorithm about corners and edges on the cube, because these are the signals, the important things that we definitely want to keep. So as a next step in our research, we put spikes on this cube. We call them normals in geometry processing. And by looking how the normal changes from one side of the cube to the other, we can actually determine whether there should be a corner or an edge that should better not be averaged or touched. We're mathematicians, so our result, of course, is a formula that relates the blue normals to the red signals. But instead of delving into this, let's rather see it in action, shall we? So same setup as before. We have the distorted cube on the upper left and the target on the lower right. And now I'm going to show you the distortion errors in red, so you can really follow the process. And already in the first couple of iterations, this is going down tremendously. So looking pretty good, and given some more time, we actually arrive at this nice clean cube. Question, is this a scientific success story? In a way, yes, sure. Robocar can recognize the cube. I got my PhD, great. But in a way, we knew what we were looking for here, right? We knew we started with a smooth object with some corners and edges. So let's maybe look at a more realistic scenario. So here's robocar driving down a nice curvy road, but then suddenly a giant rabbit steps onto it. Robocar starts the algorithm, it's running, and depending on how long the algorithm runs, the rabbit will look like one of these variations. And if you focus on the rabbits, you will see that the noise is actually going down, which is good. We want to get rid of this noise, these distortions. But look at the ears of the rabbit. While the first one still has quite some detail, these details are also getting lower. So the signal the thing that makes the rabbit a rabbit, are also going down. And that's really my take-home message here. We cannot reduce noise and keep a sharp signal. And I hate to bring the mood down, but that's something that science, new algorithms, new technology simply cannot solve. We have to take this knowledge that we have the problem, we have to take it into discussions whether we want to replace imperfect human drivers with imperfect mechanical drivers. These mechanical drivers will make different errors than the human ones, but they will make errors nonetheless. So we have to have a debate where to go with this technology. And I hope that after my talk, you can enter this debate in a more informed manner. And with that, I'd like to thank you so much for your kind attention.